Good morning. This will be a video from 13.8, finding absolute extrema, absolute max and mins. Okay, I'm going to go over example 5 from the book from page 945. And then if you need another example, I'm actually going to go over another example if you need it. You don't have to watch both. Okay. So what we're doing here, first of all, I want to compare this to what you did in a previous year. You might have some kind of a function just to visualize, maybe from A to B, okay? And maybe your function looks like this. Okay, so you would test inside your interval. You'd test where your derivative equals 0. That's a potential max or min. But then you also had to test the endpoints. Okay, so this is when we're finding absolute extrema on an interval. Okay, and once you analyze this would be an relative minimum. It also ends up being your absolute minimum. This one, well, even if that didn't stop, maybe that keeps going up. Okay. But at the end of your interval, this ends up being, it's not a max or min of your function, but if you're finding the max and mins, the absolute extrema on this interval, that would end up being your absolute max. This one you have to test also, even though it ends up not being an absolute max or an absolute min, okay? So you have to find where your derivative equals 0 or is undefined to find any possible max or mins on your inside your interval, but then you also have to test the two endpoints to see if one of those might have a value that's bigger than or smaller than any extrema on the interval. Okay. Now, when we have a function of two variables, your domain is actually a region. So here's this problem. You've got f of xy is equal to sine of xy. So there's your function, and this is going to be some sort of a surface, but you're finding it not in an interval from like A to B, but it's on some region. So here our region is going to be x goes from 0 to pi, and y goes from 0 to 1. Okay, so usually we'll draw the region. X goes 1, 2, 3, and then pi is a little more than 3, and 1. So here's our region. Okay, so first we're going to do our second derivative test, find our x derivative, which is going to be y cosine of xy. Find your y derivative, x cosine of xy. Okay, you're going to set both of those equal to 0. Okay, this is 0 when y equals 0, or when xy equals cosine of pi over 2 is 0, correct? So when xy equals pi, okay? And then this one will be 0 when x equals 0, or when same thing, xy equals, I'm sorry, not pi, pi over 2, right? Cosine of pi over 2 is 0. So xy would be pi over 2, cosine of pi over 2 would be 0. Okay, now we have to look at this case, case 1, where y equals 0. Well, what happens when y is 0? Well, when y is 0 in this, we need both of these to equal 0 at the same time to be a critical value. So if y is 0, we're going to have cosine of 0, no matter what x is, cosine of 0. Well, that's 1. So in order for this thing to equal 0, x would have to be 0. So case 1, if y is 0, then x also has to equal 0. So you've got the point 0, 0. Okay, and then case 2 would be when xy equals 2. I'm sorry, xy equals pi over 2. Xy equals pi over 2. Well, if xy is pi over 2, then you know that x and y, neither of them can be 0. And if xy is pi over 2, that satisfies making both of these 0. So that works also. So that would be any point Your next critical value would be any point, let's say x comma, if you solve this thing for y would be x over, or pi over 2x. Okay, so you have a critical point here, and then you have a critical point basically everywhere along this curve. And this thing is a hyperbola, right? Okay, it's one of those weird hyperbolas that goes like this. Okay, so now let's test. We've got this point 0, 0. Is that in our interval? Sometimes our only possible max or min, our only critical value, isn't even in our interval, so we can disregard it because we're only finding absolute extrema on this interval. But 0, 0, okay, we have to test 0, 0. So what's f of 0, 0? Plug that into your function. Sine of 0 times 0, you get sine of 0, which is 0. Okay, so this point right here is a possible max or min. And then we have everywhere along this thing. This hyperbola. So this hyperbola is going to go something like this. It's going to go somewhere like this. So let's figure out what happens. Okay, so let's say when y is 1, so where does this hyperbola cross this top boundary? So when y is 1, x would have to be pi over 2. So that would be pi over 2 comma 1. And that works because x times y will equal pi over 2. Okay, and then this is going to cross over here somewhere. Where does this cross? Well, we know that x value is pi, and when x is pi, y would have to be 1/2. Okay, and everywhere along this curve, f of, would be f of pi over 2 comma 1, would be f of pi comma 1 over 2, and it would also be f of everywhere along here where you've got f of your x value, and then your y value would be pi over 2 over x. Okay, so that would be pi over 2x, and that's along the curve xy equals 2. I'm sorry, we know that, but we'll say on the interval, okay, x goes from pi over 2 to pi. So x is between pi over 2 and pi. Okay, so this value right here will be sine of x times y, which is sine of pi over 2, which is 1. This one, you'd get sine of pi over 2 again. Here, you're also going to get sine of pi over 2 equals 1. So this right now is winning for your max. It is important to know not just what the max is. If this ends up being your max, absolute max, we need to know everywhere where it occurs. And it basically occurs everywhere where xy equals pi over 2, and x is between pi over 2 and pi. Okay, so now we have to basically test the endpoints. Remember here, we test the interior of the region, but then we have to test the endpoints. But our endpoints aren't endpoints, they're boundaries. So we have to test along this boundary, along this boundary, along this boundary, and along this boundary. Okay, so I'm going to call this L1, L2, this down here will be L3, and this will be L4. Okay, so we have tests along here, along here, along here, and along here. Okay, to find out if our function, when we plug in any point on this region, if we get a value that's bigger than 1 or smaller than 0, because right now these are the values that are winning. 1 is winning for the max, 0 is winning for the min. Okay, so let's test along L1. Okay, so what do we know about L1? So on L1, along here, we know that our y value is always 1. And we know we're looking at this when x goes from 0 to pi. Okay, so there's L1. Okay, x goes from 0 to pi. Now let's look at our function. Our function f of x comma y, but we can simplify that because we know everywhere along this boundary line, the y value is 1. So we can call it x comma 1. We also can simplify our function because we know y is always 1. So it's always going to be sine of x times 1. Okay. Now we have to know this function along this top boundary line, where is it maximized? Where is it minimized? Okay. Oh, sorry, that's not x. That's sine of x. So f of x comma 1 is going to be sine of x times 1, so sine of x. Well, we know what a sine function looks like. As x goes from 0 to pi, it looks like that. Okay, so it's maximized at pi over 2. So the max on this interval from 0 to pi is going to be at f of pi over 2 comma 1, and that's going to be sine of pi over 2, which is 1. Okay, we actually already have that point because that point is this point right here. Okay, so that actually looks like probably the max along this region. And we also know this is minimized here and here. So f of 0 comma 1 and f of pi comma 1, because that's going to give us sine of 0, which is 0, and that's going to give us sine of pi, which is 0. Okay, so the 1 was winning for the max, still is. 0 is winning for the min, still is. Okay, we just found a couple more places where our minimum might occur. It occurs here, and it occurs here. So at this point, our value of our function is 0. At this point, the value of the function is 0. At this point, the value of the function is 0. And everywhere on this point, and everywhere along here, the value of our function is 1. Okay, let's test L2. L2 is going to be this down here. I wrote it up there, but it's this entire line segment here. So L2. And on L2, we know x is constant. X is pi. We also know that y is going from 0 up to 1. Okay, so our function, we can simplify. It's still f of xy equals sine of xy, but we know that the x is constant at pi, so we can call it f of pi comma y, which is going to be sine of x times y, pi times y. And this is as y goes from 0 to 1. So when y is 0, we've got sine of 0. When y is 1, we've got sine of pi. So we're really looking at this thing, basically sine of 0 to sine of pi. Okay, sine of 0 to sine of pi. Again, we're looking at the sine function, the first curve of the sine function, right? 0 to pi. Okay, so we're going to get f of pi comma 0. Y goes from 0 to 1. Okay, so when y is 0, I'm going to have that right there, and we get that will give us sine of pi times y, so pi times 0, which is 0. And then this point right here, when y is equal to pi over 2, so pi comma pi over 2. Sorry, that's not sine. That's pi comma y would be 1/2, right? Because we need to get pi over 2. So that's going to be y would be 1/2. That's going to be sine of pi over 2, which is 1. And then f of pi, notice x is always on this line, in this boundary. We already said x is always pi. So these are all, x is always going to be pi. And the y goes from 0 up to 1. And that's going to be sine of pi, which is 0. Okay, so we just have a couple more places. We have a 0 again, a 1 again, a 0 again. Okay, so now we have to test this boundary down here and then this boundary. So on L3 is here. We know that the y value is always 0, and x goes from 0 to pi. Y equals 0, and x goes from 0 to pi. This is a little bit easier. Our function is f of x comma 0, because we know the y is always 0 on this boundary, equals sine of xy, sine of 0. So everywhere along here, we get a value of 0. which right now that's our min. It's occurring in a bunch of different places, but that's our min. So it's occurring everywhere along this entire boundary. So along the x-axis as x goes from 0 to pi. Okay, our fourth boundary, L4, we know that x is always 0, right? Along here, x is always 0 and y goes from 0 to 1. So we've got sine of, we've got f of x is 0, so 0 comma y, which is equal to sine of xy, so 0. Okay, so we have 0 along here. So everywhere along this, our value of our function is 0. Okay, so it looks like our absolute max is going to be 1, and it occurs everywhere along here. Let's just double check. Let's find everywhere where we found a 1. 1 is pi over 2 comma 1. Okay, that's covered if we talk about this curve here. Where else? Here. Pi comma 1 over 2. That's covered if we look at this curve. We don't have anything there. And then going back to where we actually used our second derivative test, we said that is equal to everywhere along that curve, xy, or xy equals pi over 2, we got our max of 1, and that covered all of these points. Okay, so sum it up. Let's give our answer. Our absolute max is equal to 1, and it occurs along the hyperbola xy equal to 1, where x goes from, let's double check here, x went from pi over 2 to pi. So we don't want this entire hyperbola, we just want pi over 2 to pi. Okay, there's your absolute max. Our absolute min is equal to 0. This occurs at a lot of places and occurs at, well, we know it occurred at 0, 0. We found that up here. Critical point was 0, 0. F of 0, 0 was 0. It also occurred at 0, comma 1. So there's our 0 there. 0, comma 1, pi, comma 1. Okay, anywhere else? Pi, comma 0. Do we have that one? Oh, pi, comma 0. Pi, comma 1. Oh, we already have that one. And where else? Okay, along the x-axis. Remember, it was here everywhere along the x-axis. So along the x-axis and along the y-axis. Okay, so and along the x-axis, where x went from 0 to pi, and along, sorry. So these 4 points, and along the x-axis where x goes from 0 to pi, and along the y-axis where y goes from 0 to 1. Okay, it's kind of a pain to write all that out, but you want to give the absolute max and the absolute min in all the places where it occurs. Okay, if that made sense, if you followed, you can stop here, go on and get started on the homework assignments. So homework assignment, which was the rest of 13.8. Okay, if you want to stick around, stick with me, I'm going to do one more example. I'm going to do number 43 from the book. Okay, which was not assigned, but I'm going to do 43. Okay. Which is on page 947. 43. Okay, so you've got f of x comma y equal to 3x squared plus 2y squared minus 4y. And this is on the region bounded by the graphs of y equals x squared and y equals 4. Okay, so I like to draw the region. So this is just a parabola, 1, 2, 1, 2, 2, 3, 4. Okay, this is the point 2 comma 4. This is the point negative 2 comma 4. Okay, it's a little lopsided, but you get the idea. So on this region here, so first thing we do, we have to check if there's an if there's any critical points inside the region. So we find the x derivative, which is 4x. And we're going to set that equal to 0. So x better be 0. And then we're going to find the y derivative, which equals 4y minus 4. Set that equal to 0. So you get 4y equals 4 or y equal to 1. That works out kind of nicely. Your only critical point is 0 comma 1. And f of 0 comma 1 is equal to, plug that into your function, you get 0. 2 times 1 squared is 2 minus 4 times 1. So 2 minus 4 is negative 2. Okay. Now, what we could do, we could find that d value, that determinant, and figure out if this is a max, if it's a min, if it's a saddle point. But you don't really have to do that because this question is just asking us to find our absolute max and mins. Okay. So all we have to know right now, this is a possible max or min. We have to compare this value to all the values that we find around the boundaries. Okay. The nice thing about this is we've only got 2 boundaries to find. We've got L1, I'll call that this, y equals 4, between x equals negative 2 and positive 2. And then we've got this. We'll call this one L2, which is y equals x squared, as x goes from negative 2 to 2. Okay, so let's check on L1. So on L1, we know that our y value is constant at 4. And we know that x is going from negative 2 to 2. So our function we can simplify is f of x comma 4, because our y value is constant at 4. So plugging this into our function, going back to your function up here, 3x squared plus 2 times y squared. So 3x squared minus 2 times, well, our y is constant at 4, so 4 squared minus 4 times 4. Okay, 2 times 4 squared minus 4 times 4. Okay, and this comes out to be 3x squared, so minus 2 times 16 minus 30, oh, I'm sorry, this should have been a plus. So plus 32 minus 16, so that gives you plus 16. Okay, so we're testing this thing. So this is the value of our function as x goes from negative 2 to positive 2. Now this is where the reason I did this one, this gets a little tricky. We need to find the maximum of this thing on this interval. Okay, you can kind of guess this is a parabola opening up. Okay, let's see. Okay, this is this is a parabola opening up, so you know it's minimized at when x is 0. So f of 0 comma 4 would be equal to 16. Okay, and it should be maximized at the furthest extremes. So you know that this thing's a parabola opening up with the vertex at x equals 0. So let's test the 2 endpoints, f of negative 2 comma 4 and f of 2 comma 4. Okay, plugging those into your original function, or plugging them into here, the simplified function, since we already plugged that in. So you're going to get 3 times 4, 12 plus 16, that gives you 28. Okay, this one will also give you 28. Okay, so this is winning for your max, at these two locations. This one we know is not going to be an absolute min because we already have a value that's lower. Okay, let's try on L2. And on L2, we know that y is equal to x squared. And we know that x is going from -2 to 2. Okay, so our f of x comma y, but y is x squared, so I'm going to say f of x comma x squared equal to, now we're going to go to our function. Remember this function up here. It's going to be 3 times x squared. We're going to plug in an x squared for each y. So that's going to be 2 times x squared squared, 2x to the 4th minus 4x squared. Okay, so we get 3x squared minus, or plus 2 x to the 4th minus 4x squared. Okay, and what this comes out to be is 2x to the 4th minus x squared. Okay, we could factor out an x squared from both of these. But do we want to do that? I don't know that we want to do that. This is a goofy one because this function, we have to find the max and minimums of this function on this interval. Okay, so you might be able to figure out, test the endpoints, but where on the interior of this is this a max or a min? This is a little harder to do. Okay, so let's say this is some function. Let's just call it g is equal to this. We want to maximize this on this interval, -2 to 2. Okay, so what we're going to do to maximize or minimize a function, you go back to your techniques from last year. G prime would be equal to 8x cubed minus 2x. Set that equal to 0. Okay, so that's going to be 2x times x squared minus, 4x squared minus 1. Equal to 0. Okay, set equal to 0. So you've got x equals 0, and you've got this thing. So 4x squared minus 1 equals 0. So that's the x squared equals 1/4. So x would equal plus or minus 1/2. Remember what we're doing. We're just trying to maximize and minimize this by our function. Okay, I don't know what I call it g. We could call it f because it's really just our f function. It's our f function that's specific to this thing right here, y equals x squared. Okay, so now let's make a number line when x is 0, when x is 1/2, when x is -1/2. And let's also put in our endpoints of 2 and -2. Okay, if this is f prime is 0 here, here, and here. Is f prime going to be positive or negative on these intervals? Okay, so f prime, let's say when x is 1/4, 8 times 1/4 cubed minus 2 times 1/4. That one comes out to be negative. Okay, so you've got negative, let's say -1/8, or let's say -1/4. So 8 times -1/4 cubed, that's a -1/8 minus 2 times negative, so that becomes a positive. This is going to be positive. Okay, bigger than 1/2, let's plug in 1. We get 8 minus 2, that's positive 6. 6, which is positive. Okay, -1, I'm going to get -8 plus 2, so that's going to be negative. Okay, so your potential maxes are going to happen at the endpoints. This is a potential min. This is a potential max. This is a potential min. Okay, let's just check all those points. So we want to find f of, we've got a lot of them, f of when x is, we already tested the endpoints, right? No, we didn't. -2, comma, and remember y is x squared. So if x is -2, y is 4. Like we are also going to have this endpoint, f of 2 comma 4. And actually, we do already have those. This point occurred here because that was also on the line. So these equal 28. Now we've got f of -1/2, comma, that thing squared, so 1/4, and f of +1/2, +1/4, okay? And that's equal to something, and then we have f of 0, 0, and f of 0, 0 will equal 0, because plugging into your function, everything would be 0, okay? And f of -1/2, comma, 1/4, so your x value would be -1/2. This comes out to be, this is kind of messy, but let's just do this on a separate sheet of paper. Okay, so your function was f of x comma x squared equal to 3x squared plus 2x to the fourth minus 4x squared. Let's plug in a little -1/2, comma, 1/4. So you get 3 times -1/2 squared is 1/4 plus 2 times x to the fourth. So 2 times 1/16 minus 4 times 1/4. That's going to be 3/4 plus 1/8 minus 1. So 3/4. That's 6/8 minus plus 1/8. That's 7/8 minus 8/8, which is -1/8. Okay, -1/8. Okay. And since this is an even function, meaning every time you have an x, it's squared or to the fourth, plugging in +1/2, you're going to get the same thing. So -1/8. Okay. So it looks like this wins for our max. That's our absolute max. We don't have any value of our function that's bigger than 28. Okay, we have to test all these places. We had the 16, the 28, the 28. We had the 28, the 28, the -1/8, the -1/8, and the 0. But don't forget, we also had this -2 that we found when we did the second derivative test. Okay, so this wins for the absolute min. This wins for this down here wins for our max. Okay, so writing up your answer. Absolute max is equal to 28. Occurs at ±2, comma, 4. There's your absolute max. Absolute min equals -2, and it occurs at 0, comma, 1. Okay? So these problems are, I don't know, there's a lot to them, and I just went through two really kind of more complicated ones just because I wanted to show you what to do when it gets complicated. A lot of the ones that you'll have for homework will not be this complicated. All right. Thank you all for watching. I will see you soon.